So let us start today's session of live session 9. Uh, this session will cover mostly on the topic of coating and additive manufacturing part, and mostly we'll go through the theoretical aspects of different techniques, whatever is available in coating and additive manufacturing. So let us start. So in question one, it asks that which of the following statement is correct regarding zinc alloy electroplating technique. So if you see, there are different kinds of electroplating technique. Uh, there is like one is copper plating and another can be zinc alloy plating. Now, if you see, electroplating is a very common kind of process in industry. It basically involves the use of an electrical current to to bind the metal particles onto a surface, and it can be a possible replacement for manufacturing process something called cadmium coatings, which can eliminate workplace exposure to cadmium and cyanide, right? And this the corrosion resistance can be as good as cadmium for this zinc alloy electroplating thing, and it can have better wear resistance also than cadmium. And the coating metal is basically evaporated and partially ionized before being deposited on the substrate in ion vapor deposition. So if you see different statements here, it says first statement says it involves the use of an electrical current to bind the metal particles onto a surface. So yes, this is true for zinc alloy plating. In zinc alloy plating, you use some electrical current to bind the particles. So this is true. And in the second statement, it says the coating metal is evaporated and partially ionized before being deposited on the substrate. This is basically whenever the coating metal is getting evaporated and it's getting ionized before being deposited on the substrate, it is this is mainly called something called ion vapor deposition. So this is separately a different new technique. So in terms of zinc alloy electroplating technique, this statement will be false. And next, in statement C, it says that it is an electrolytic process that relies strictly on chemical reactions to bind metal particles onto the surface of an object. Now, in zinc alloy plating, it is an electroplating process. If you see in copper plating, yes, it is an electrolytic process which relies on these chemical reactions, and because of these chemical reactions, the particles bind on the surface of objects. So, statement C is mainly the statement for copper plating. So, in terms of zinc alloy electroplating technique, this statement is again false, right? So A is true, B is false, and C is also false. We are looking for zinc alloy electroplating technique. Now in question 2, we need to figure out which one is correct in terms of physical vapor deposition. So if you see in physical vapor deposition, uh, it's like initially a cleaned kind of workpiece is placed in a vacuum chamber, and after after you keep it in a vacuum chamber, then your chamber is getting heated, and maybe some kind of plasma is created from an inert gas such as argon, and then the workpiece is first plasma etched to further clean the surface, and then what happens is the coating metal is then forced into the gas phase by either evaporation or sputtering or iron plating. So the basic mechanism of physical vapor deposition is coating metal forced into the gas phase by either evaporation or there can be some kind of sputtering, or there can be kind of iron plating method, right? So yes, in terms of physical vapor deposition, this statement is true, and this statement is also true because it is heated in a vacuum chamber. Otherwise, it will react with air, and there can be some kind of oxidation if it reacts with air in atmosphere. And then in the third statement, it says that it relies on electrolytic process. So of course, this does not rely on electrolytic process. Electrolytic process, it's mainly for those plating techniques, like as I said, for copper plating it depends on electrolytic process and some kind of displacement of ions between cathode and anode, and because of chemical reactions the metal particles bind onto the surface of an object. So this is true. This is any questions till now?
No, sir. We can proceed for the next question.
Okay. So question three is a simple numerical kind of thing, depending on whatever is covered. It says that to develop a 3D printed part in a Nd:YAG laser of, so your power is provided. So the laser power is provided, which is P equal to 2 kilowatt. And then it says that there is a 500 mm per second scan velocity of the laser. So you have your laser scan speed as, let's keep it small v, 500 mm per second, and you have some build rate volume of, you have some build rate volume of, okay, uh, this is a wrong data maybe. This is kind of absurd kind of data. Let us take it as maybe 20, means it is very small in terms of build rate volume for additive manufacturing process. So let's keep it 20 centimeter cube per hour. Or else we can keep it like this, no problem. So your build rate volume is 100 cube per second. And then it asks that what will be the layer thickness of the deposited material if the hatch distance is of 0.2 mm. Now if you have the build rate volume, what is the build rate volume? You have your scanning speed, right? You have your scanning speed, that should be multiplied with your hatch spacing. Let's say that is some y, and that should be multiplied with your deposition thickness. Let's say that is z. So your build rate volume is 100 cube per second, and then your scanning speed is 500 per second. That into it's given, the hatch distance is given 0.2, that into z. So you need to find out what will be the deposition thickness in terms of Yes. That's why I kept it in 100 only. So it's coming a very good number and fine. So we are getting some deposition thickness of 1 and then it asks that we need to estimate the energy density required to make the product. So in terms of energy density, what it will be? In terms of energy density, what it will be? It will be simply power by your build rate volume. Is it not? So you have your power as 2 kilowatt, which is 2000 watt, that is joule per second, and then you have your build rate volume of 100 cube per second. So it will be coming in terms of joule per cube. Right? So it was a simple, short kind of numerical. There should not be any confusion as such. Next, in question 4, we need to basically match the followings of different kind of techniques and what are the mechanism of these techniques. So there are techniques like cold metal transfer, gas metal arc welding, stereolithography, and laser sintering. Now, now if you see cold metal transfer, it's actually a part of gas metal arc welding. So in principle, it works at reduced welding current, and generally you retract the welding wire at a short circuit condition and ensure a drop by drop deposit of the weld material. So for cold metal transfer, it basically relies on this drop by drop deposit of weld material. But if you see in gas metal arc welding, their wire is continuously moving forward into the weld pool. So in gas metal arc welding, you see a continuous movement of the weld electrode. So let's write it here. For cold metal transfer, you'll see drop by drop deposit. Gas metal arc welding, you'll see continuous movement of weld electrodes. And now in CMT, it's like the wire is retracted, the instant current flows. So basically, what happens? It breaks the arc, right? And because of it breaks the arc, the metal droplet detaches from the filler, and it can fuses with the steel molten base metal, right? So when you are breaking the arc, so whatever the metal, whatever the arc is there, it kind of droplet making in between that arc, and because of the droplet detachment from the filler, it fuses with the uh, molten base metal, and again the wire moves forward and to create another arc, right? So all these phenomena happen several times in each second. So basically, if you see cold metal transfer, it provides a controlled method of material deposition by uh, we say it sophisticated wire feed system at low thermal input, right? In gas metal arc welding, transfer of molten metal happens from consumable electrode to the weld pool with some kind of secondary factors like there can be some shielding gases, there can be composition of electrode can also affect, the diameter of electrodes can also affect in gas metal arc welding. So there are kind of different secondary factors, but yes, there will be continuous movement of the weld electrode. Now, in terms of the stereolithography and laser sintering, what can we see? In stereolithography, this is widely recognized as a 3D printing process, which is a laser-based process, of course, and this works with mainly with photopolymer resins. So yes, this for stereolithography works on photopolymer resins, and it reacts with laser and finally cure it to form a solid, right? It is generally accepted as being one of the most accurate 3D printing process with excellent kind of surface finish. Now, in terms of laser sintering, it is mainly used in, it can be used in polyamide, or maybe it can be used in titanium and rubber like materials. So the laser basically fuses powders while the rest are as loose powders. So after one layer, after you are melting one layer, a new layer of fresh powders is sprayed over the surface by a roller. Mainly, there are no support structure is required, and the unsintered or melted powder is used as a support material in laser sintering. So, for laser sintering, we sinter mainly the metallic powders, and you need to have some powder bed system for all kind of sintering. So you need to have some powder bed system. So it's like if you have a if you try to figure out how does it look like. So you have a base metal, base not metal. You have a base like this, and then you have some kind of roller over here. So initially you sprayed the powders and then roll it over it, and then you have a laser which is coming onto the powder bed, and it can have a scan speed of say some velocity, and it scans throughout all the powder bed, and it makes one layer, and then again you sprayed your powder over that layer, and then again you roll it over, and then again you melt through the laser. So it's basically layer by layer deposition. What is the basic and primary mechanism of additive manufacturing? Okay, let's move to the next question then. Here also different kinds of additive manufacturing we have. PBF is basically powder bed fusion, and then you have binder jetting, then you have material jetting, and then something called direct energy deposition. So here, as I was saying in powder bed fusion, I already discussed it. So of course, in powder bed fusion, you have to have powder bed which will be sprayed and then it rolled, and then the laser comes out and scan it and makes one layer, and then again you sprayed the powder, and then again you melt it and makes another layer. And in terms of if you see binder jetting, in binder jetting what happens is like materials selectively deposit onto the powder bed, so bonding these areas to form a solid part, right? The common materials are like it can be metals, it can be sand, it can be ceramics in granular form. So in binder jetting, there is no need of support structure. So binder jetting and even in powder bed fusion also does not require it. Any support structure is not required. And then in material jetting, you have a print head similar to what do you say, inkjet printing. So you have some kind of print jet which distributes the droplets of a photosensitive material that solidifies under UV light, ultraviolet light, and you have to have support structure for your material jetting. The example can be like uh, thermoset polymer, photopolymer, acrylics in liquid form. So in material jetting, it is droplets of photosensitive material that solidifies under UV light, and here support structure is required. Now, if you see in direct energy deposition method, it mainly consists of a coaxial feed of powder or wire, which exposed to a laser, or it can be an electron beam. Mainly, this laser and electron beam is used to form a melted or sintered layer on a substrate, right? So powder deposition is synchronized with the heat source. It does not use powder bed system. It does not use any kind of powder bed system. So if you see how does it look like, uh, let us try to draw something. So of course initially you have a substrate kind of thing, but that is not a powder bed. And then you can have some kind of hooper here, which is the source of your powder. It can be amorphous powder, it can be some some single metal powder. Amorphous powder is mainly you are alloying different powders and making some uh, the final product will be some kind of alloy formation, and basically you want to enhance ultimately the strength and ductility in terms of structural performance, right? So you can have amorphous powder, you can have pure metal powder, and there you have some kind of laser head where you have some kind of slots, and one slot will be connected with your this hooper system, through which it can come out, the powders can come out. And as I said, this heating thing and this spreading of powders are all synchronized. So whenever it is getting spreaded, at the same time your laser scanned over there, and before getting deposited it's melted. So what happens is, before deposition itself, the powder melts, and it deposit in terms of you can say it in terms of a melt layer or maybe semi solid layer, by the time it gets deposited over the substrate. Okay.
Excuse me, sir. Sir?
Now in question 6 it says, which of the following is a laser based 3D metal printing technology that is not based on powder bed? So that I already told that all kinds of sintering process, whatever is there, like I mentioned here, like selective laser sintering, or it can be selective metal melting, or it can be direct metal laser sintering. So there, all the laser sintering process, the laser fuses powders while the rest are as loose powders, right? As I was saying initially, it will be all loose powders spreaded over, and then the laser scans all over that powder bed, and it's like wherever at some places it will be fused, and at some places uh, it will be at base state. It will be at as a loose powder. It will be stay there, right? And after one layer, then new layer of fresh powder is sprayed over the surface by a roller, and that's how it makes the product, right? Layer by layer. But in terms of direct metal deposition, as I was saying, it uh, is kind of a coaxial feed of powder or wear to a laser or electron beam, whichever you are using, to form a melted layer on a substrate. So basically, scaling up of this direct energy deposition, if you see, it is easier and more cost effective to produce larger parts, right? And direct energy deposition can also be used to coat existing structures. Uh, Important application, there can be some kind of uh, repairing, or you can, if there is any cracks kind of thing, you can repair by direct energy deposition, or any kind of defects you want to repair, right? So here, of course, this direct metal deposition is not based on sintering processes primarily. Powder bed fusion system.
Sir?
Any question?
Yeah, yes, sir. Can you please brief about what is meant by powder bed? Whether it is already completely filled with metallic powders, or we each cycles we replenish that bed with the powders during the each layers of the materials.
So you have a kind of, yes, initially you can have like bed like structure. Over there you initially sprayed your loose powders like this. So it's all loose powders initially. So as of now you are not melting it, or any kind of deposition is not happening. So you have all kind of loose powders. You sprayed it over the powder bed, and then you use a roller system to get some uniform dispersion, right? Uniform dispersion of the powder. So if you have a roller kind of thing, and you roll it over there by some rolling pressure, so it can form some kind of, you can say it like green compact. So in green compact, what happens that you have some loose, uh means you know what is powder compaction, right? So in powder compaction, what happens is you have a punch, you have a die, and you keep your loose powders in your die, and if you punch it by some uniform pressure, you can form some thick green compact, which of course does not have that strength what sintered thing have, because of that temperature and pressure generation, right? And when you complete this rolling system over the powder spread, and then you come with this your laser scanning system, and then you melt your this powder bed. Uh, let's say we remove this roller, and from here we start. This is your laser head, where the you are scanning this powder bed, and it is getting moved. So initially there will be your heat flux generation. All over the others, it's still in loose powders. So initially it is getting melted here, and then with time, when it moves at a certain scanning speed, it scans like this. So melts the it melts one, as I was saying, yeah, it can be like hatch. This is one hatch, and then you scan it over here. This is one hatch. Then you scan it here. This is one hatch, and then like this, like this. So you make one layer with this kind of scan strategy. So this is called hatch spacing. These things. So depending on your heat flux, there your like if your heat flux is too low, you can have molten pool like this. Here you can have some kind of defect formation are already going on, right? So it is like whatever molten pool is getting generated, it cannot fill that empty space. Now if you are using some kind of high heat source through the laser, your molten pool gets wider, and you can create some kind of overlap. Are you getting my point?
Yes, sir.
So it creates some kind of wider melt pool. So there can be different kinds of process parameter. It also depends on your scanning speed also. If you are moving it too fast, the heat will generate, whatever heat will be generated, that will be not too high, right? So if your scanning speed is high, your heat generation will be less. So depending on your heat generation or how fast you are cooling, basically your cooling rate uh, also affects your structural performance, right? So depending on your cooling rate, it can have some fine microstructure. Yes, of course, any kind of additive manufacturing, if you see, uh, there can be always some hot tear formation or crack formation, because somewhere you are still at heating state and somewhere it's already cooled. So all kind of this residual stress gets generated and this gets stored, and these are very detrimental for your structural performances. So yeah, uh, what I was saying is, for any kind of sintering, it's not initially melted, so it's all loose powders all over, and then you start scanning through your laser, and then you melt and solidify, and then when one layer already completed, and then you again, it's some kind of, you place the powder again over this layer, and again you scan. But this is not the case for direct energy deposition. So direct energy deposition have some kind of synchronization between this laser scanning and spreading of powders. There is no concept of this powder bed. So as I was saying, so from the from the laser head itself, there is some slot, there is some kind of slot through which you spread your powders over here, and at the same time it gets melted due to the laser, and it, whenever it getting deposited, it is deposited in terms of a melted layer, like this. Got my point?
Yes, sir. I got the point about direct metal deposition, sir. But I have a doubt in the powder bed based systems. What will be that process after this first layer is completely full? Because we have just one layer of the powder. We have rolled it, and now we melt it. And what will be the next step, sir? How each layer by layer we proceed? In direct metal deposition, continuous deposition happens from this one laser source and this one. But what happens in the powder bed based systems like sintering? What will be the next layer? How it will be deposited over the molten layer?
It's uh, maybe you can see some video. Maybe I'm not able to exactly draw the schematic. Let me try once. Just so let me try to draw some. It will be 3D, of course. Uh, Still, let me try. So, So this red one is a chamber. You can see it as a chamber, and this blue one is what I was saying is a powder bed. Okay,
Yes,
and you can have some kind of mechanism. You can have some kind of mechanism through which this powder bed can move downward. Okay, and
yes, sir.
uh, then you can have some roller. You can have some roller like this, and then there can be some kind of laser system. So you can have maybe this lenses, and then you can have some kind of mirror through which ultimately it is getting scanned, right? And
Yes, sir.
whenever say initially it is so this is your complete volume of the maybe uh, the chamber volume. So initially, let's say this was at a height of h1, and then the spreading and then rolling, and then initial this laser scanning happened, and you formed one layer, and then this powder bed, it comes downward a little bit, depending on your whatever thickness you want, depending on layer thickness. This powder bed comes downward, and then again you sprayed the powder, and then you rolled it again, and then you again scan. Yeah, means there is some mechanism of this changing the powder bed height depending on your layer thickness.
Yes, sir. I understand that, sir. But how each layer will be how each layer will be joined together, fused together with each other, sir. That's my question.
Hence initially if it is one layer, so over that layer you are spreading powder again, and then you are again melting and solidifying it, and this is forming one layer, and over this layer only you are again spreading it.
Okay. So with each layer, each layer is allowed to melt and solidify. On
Right, right. And because of this thing, so you are remelting and resolidifying. So initially it was one layer already formed, and then you are spreading powder, and you are you wanted to melt this layer only, right? But because of this heat generation, the down layer also get affected because of that heat generation. So it's like remelting and resolidification. And whenever there is kind of remelting and resolidification, you are uh, you are having residual stress all over the material, and because of that residual stress, there can be some kind of fracture occurs.
Yeah, okay, sir. And then the other leftover powders, they will be cleaned afterwards. They'll be removed. Only the intact formed layers will be used from the product.
Right, correct.
So, this is now understood, sir. Thanks.
Okay, should we move
Sure.
now? This is in terms of ion vapor deposition. which of the following is true for iron vapor deposition. So if you see in iron vapor deposition, it's like whatever it is, whatever the coating metal it is it is getting evaporated and it's partially ionized before being deposited on the substrate. And the system consists of a steel vacuum chamber, or maybe there can be some kind of pumping system. There can be some kind of evaporation source, maybe some kind of high voltage power supply. So the ion vapor deposition consists of this kind of systems, and yeah, health and safety risks can be greatly reduced as compared to this cadmium electroplating, and the process significantly reduces this generation of hazardous wastes, and it potentially eliminates the need for spatial pollution control system. So yeah, so in terms of ion vapor deposition, so the statement one says it results in a thin uniform coating that is much less likely to require machining after application. Then it said it does not require a vacuum chamber, but yes, it is require a vacuum chamber. So this is false. Then it says the coating metal is evaporated and partially ionized before being. Yes, this is true. And in terms of plasma etching, is it true or false? So these two are for PVD.
Yes, sir. For
P-
PVD, it's good.
Yeah. Statement A and B.
What about C, sir?
PVD. Sorry.
Option C.
Option C is true for in terms of ion vapor deposition. So here the coating metal is evaporated and partially ionized before being deposited on the substrate.
So the answer is C.
Yes, answer is C. Only true. Right. Okay. So this is the last question, and this is again some kind of similar thing whatever we covered till now. So it's on direct energy deposition. There is one statement which is a coaxial feed of powder or wire to a laser or electron beam energy source is used. Yes, this is true. So in your direct energy deposition, as I was saying, that you will have a coaxial feed of powder or wire uh, to a laser or electron beam energy source, which is used to melt or sinter over the substrate, and powder deposition is synchronized. So here both statement one and two is true.
Option C.
Option C. Okay, that's it from my side today. But yeah, it was a good discussion.
Sir, I just have a doubt on the previous question. Uh, like
Yeah.
on the thin on the layer, like how can we differentiate on the layers? I understood that the plasma etching is done for PVD. And, what about the thin uniform coating? What would happen in the ion vapor deposition, sir? What is the characteristic of the coating of the thickness, and why that A is not correct for ion vapor deposition, sir?
Hmm, hmm, hmm.
So in which case we have to go for IVD versus PVD, sir. Like any specific highlight on
Mm. As in this case, I'm not in a correct position to comment on this exactly. Uh, But yes, you were right. Means there should be some difference between ion vapor deposition and physical vapor deposition in terms of this uh, maybe this deposition thickness. I'm not sure in ion vapor deposition is it non-uniform or what. Uh, but in both the cases, yes, there is some kind of evaporation. So if you see in physical vapor deposition, also the coating metal is basically forced into the gas phase by either evaporation or this ion plating. And in ion vapor deposition also, there is some kind of evaporation.
And
And
also
there
partial ion,
also, sorry,
and also partial ionization, which is not present
yes,
there.
partial ionization. You are right. Uh, Maybe I need to check and get back to you in terms of this uniformity of thickness, whatever the comment is there,
Sure.
the C1, right?
Yeah.
Yes.
I have doubt regarding option A, like, and also what is the regarding on what basis we will be going for IVD versus PVD. That's my doubt.
Okay.
Yeah, yes, sir.
So, yeah, I will check and get back to you.
Sure, sir. Sure, sir.
Okay.
Yes, sir. Sure.
Okay.
That's it,
Okay.
sir.
Any more question?
That's it, sir. Thank you so much, sir.
Yeah. Thank you.
Thank you, sir. Have a great evening.